All right, and here we come to the issue of structure-process trade-offs. And this is the basic idea that's going to be pervasive in all kinds of information processing and in cognitive science, that any kind of representations you pick are going to make some kinds of operations or some kinds of processes easier than others. And some kinds of processes or operations are going to be easier to perform on some representations than on others, right? So there's always going to be a trade-off in the complexity or the structure of our representations and the easiness or complicatedness of the rules or processes or constraints that we need to perform on those representations, right? The way Marr puts it, the issue is important because how information is represented can greatly affect how easy it is to do different things with it. That's evident even from our numbers example. So we've been looking at ways to represent numbers in the overview part of this class. Marr also goes through a lot of examples with this because they're pretty easy to understand. We all have some facility with basic arithmetic, and it's a classical information processing task. So he's talking here about three representations of numbers. There's the Arabic numeral system that most of us are familiar with. And that's, we happen to work in a base 10 system where we use these numbers, right? And so on and so forth. And that's an Arabic numeral notation. This is the particular base 10 system we used, although we also looked at a base 2 system that is at the binary code where all you have are these two Arabic numerals. And he's pointing out that it's pretty easy to do arithmetic if we use these representations, right? We have well understood algorithms. Let me go through the ones that we know first, right? Let's say you want to multiply some 3-digit numbers. We all learned in school a way to do this, right? Using these Arabic numeral notations, you put one on top of the other, you multiply the ones by the ones, you put the result down here. You have to carry powers of 10 in this system. So, if we actually do this, I'm not going to do the whole thing, but that first result we'll get is a 12. So we put the 2 down here, and then you have to carry a power of 10 to the first power up here, add 1, and then you'll get 6 in the next column. I'm messing up. I'm combining multiplication and addition. But in any case, the point is you're going to have to, this is eventually going to turn into an addition problem, in which case you'll have to carry powers of 10. But regardless of my fumbling inability to actually do the problem on the spot, we all basically know a pretty easy algorithm for multiplying or adding numbers in this format. Let me actually give an addition example just because it's going to be easier to illustrate here. So the outcome of this, if we're adding them, is going to be 13. And my point here was this, that you put the 3 here and you have to carry a power of 10 up here. So it adds to the next column. And instead of getting 2 plus 3, you get 2 plus 3 plus the extra 1. So you get 6, right? That's the main point here. Note that you can do exactly the same thing with arbitrary strings of zeros and ones in a base 2 system. But if you choose to represent the numbers in this way, it's going to constrain the algorithm. Instead of carrying powers of 10, now you're going to have to carry powers of 2. Otherwise, it's going to work exactly the same way. Now, this is going to be harder for us because most of us weren't taught how to add like this. But they both use very similar algorithms, and they both work really nicely, right? His point of comparison here is Roman numerals. So I don't know if all of you know this system, but it's where, I is 1, and then V is 5, and C is 100, and X is 10. And then in order to write like 4, instead of being 4 I's, it's 1 I before V or something like that. And his point here is that that is a perfectly valid choice of representation. We can write any number like that, any integer or natural number like that, but it's terrible for doing arithmetic, right? So, try multiplying 145. I don't even know if I can write that. 145, right, times 123 in this system. Oops. Right? There's your representations. Good luck. Try multiplying these now. It's going to be extremely hard. And his point is just that one of these representations is well suited to a particular algorithm for multiplying, namely the Arabic one, while the Roman numerals are really poorly suited for doing these kinds of operations. And so again, our choice of representation is constraining what kinds of operations or processes we're able to do. Now, I do have an algorithm that will work for this. Here's my algorithm. Take each of these numbers, convert them to Arabic numerals, multiply them, get the result, and convert it back into Roman numerals. That's my best algorithm for doing this. Obviously, more complicated than the algorithm we started with, right? So there are three important points here, according to Marr. First, there's usually a wide choice of representation. Second, the choice of algorithm often depends rather critically on the particular representation that's employed. And third, even for a given fixed representation, there are often several possible algorithms for carrying out the same process. Which one is chosen will usually depend on some particularly desirable or undesirable characteristics, right? And this is going to be very much true not just for representing numbers, but also for representing language. We'll get there shortly. Let's come back to the example that we discussed in the first few classes here of choosing a random person out of 8 people in the class to win a prize. And we saw, again, a choice of different ways of representing different people in that process. And we saw that each one is going to produce a different kind of algorithm. And of course, that also depends very much on the physical medium in which we decided to do the computations. We're going to try to ignore that for the moment. We'll come back to it later. But now we're just thinking about how we're representing people and what kind of algorithms we're going to use over them. And so one of the things we came up with is that we can represent people with, sorry, I'm trying to erase this. Well, let me just leave that up there and I'll make a new one. One of the ways we came up with to represent people was using the numerals 1 through 8. And we discussed putting this on a die in particular, although you could do this on any number of devices, right? And one of the algorithms we discussed was taking a physical object and throwing it up in the air and seeing where it lands, right? Now, if you happen to have an object that can represent 8 people like this, that's a great algorithm. The example we discussed was a die with 8 sides. Throw it up in the air, see where it lands, and now we've got a good algorithm. We've chosen a person who's going to win the prize, right? We also discussed a 6-sided die, and we saw that that's going to be significantly more complicated. Why? Because now some people are going to be represented by one particular throw of the die, but then also we're going to need some way to get the extra 2 people. We're going to have to come up with a more complicated convention for representing the 7th and 8th people, and then we're going to have to still come up with an algorithm that's going to make us equally likely to pick any of the 8 people, but it's going to be a different kind of algorithm. You can't just toss this device once and pick a person. You're going to need a different algorithm. We also discussed representing people with 2 sides of a coin, heads and tails. Right? And we saw that here you can very much do this, except you're going to need 3 consecutive binary choices, 3 bits of information. The die already contains 3 bits of information, but a 2-sided coin only contains 1 bit of information. And so you're going to need a different algorithm. You're going to need 3 coin flips in order to do this kind of a computation using this representation, right? So throwing a physical object up in the air works really nicely if you have the numerals, people represented with the numerals 1 through 8. Throwing a device up in the air once doesn't work if you only have 1 bit of information represented. Instead, if you have people represented as sequences of 3 binary choices. So like one person might be heads, heads, tails, one person might be tails, tails, heads, so on and so forth. Now you're going to need a different algorithm. You're going to need 3 coin flips. Similarly, we discussed an algorithm where I sort of randomly point at 2 areas of the board after disorienting myself or something like that. And on one side of the board, I've printed 0, and on the other side of the board, I've printed 1. And again, in this system, just like the coin flip, we're going to need an algorithm that repeats 3 times. Now it's no longer going to be a throwing up in the air algorithm. It's going to be a Jonah spinning around and randomly pointing algorithm, but it's still going to need to have 3 iterations in order to get one of the 8 people that we're considering, right? So this is just a really basic point about how we choose to represent different kinds of information and what we have to do in order to accomplish things with those representations, where the 2 things really depend on one another to a great extent. Now, obviously, all of these examples also have implications about what kind of a physical device you'd want to use in order to perform these computations, if you will, or I guess random selections would be another way of looking at it. And that is true as well, but that's separate from these levels. So first, we're looking at the interdependence between representation and what you do with it. Later, we're also going to consider the relationship between what kinds of algorithms can be run on which kinds of physical devices and vice versa. That's a separate question, although the conclusion is going to be very similar. So we have lots of ways of representing, in this case, either numbers or members of the class or something like that. How we choose to represent them is going to constrain which things are easy and hard to do with them. And that's the main point here. So this is going to be true in arithmetic. It's going to be true in randomly selecting people. It's going to be true in seeing. And it's going to be true in language, right? And so I wanted to go through some of the simple examples first before we get more complex.